So the other day, you're in a meeting somewhere, and someone brings up like, hey, like our application is pretty slow in this JRuby thing. Might be we should rewrite it in JRuby. And you're taking notes, you have Slack running, you're in a meeting, you're like, I got this, I'm an engineer. So you whip up a quick script that goes like, okay, like for our application, it's very important to reverse sort an array for whatever reason. You just think that's very important, and you think that's the best way to do it. And it's like, okay, I got JRuby and JRuby installed. Let's like use both of those, update your JRuby version and then the JRuby version. And JRuby completes in way under a second. JRuby takes more than 3 seconds. And so like, okay, right. Like those JVM clowns, they were wrong the whole time. Our real good JRuby, that's real good stuff. Like no reason to reach to JRuby. And obviously, this is the end of the talk, because obviously all benchmarks are done like this. It's super easy. Everybody can do it. Not quite. For me, this is more an example of I have really no idea what I'm doing. There's so many problems with this benchmark, I can't even begin to mention them all. Like you have lots of applications running, you're on battery, you're measuring the startup and the warm-up time, which I'll get to in a second, and then does it really matter, like this reverse sorting? Is that really your biggest problem? And also, is that the fastest way to reverse sort an array? Spoiler, it's not. I don't have the time to show you that benchmark, but we'll see lots of other benchmarks. So I'm going on about the time here, and when you use time, invoke a script, this is exactly like the whole time that we're measuring here. Let's break that down. First, you have the startup time, which is the time until actually the Ruby interpreter or whatever language you're running starts doing anything. So for instance, JRuby has to start up the JVM, which can be quite slow and a drag. Then we have warm-up time. Warm-up time, especially for JVM or other sophisticated VMs like the GraalVM on the JVM, is the time that needs to optimize your code to run at peak performance. That time is also in there. And finally, we come to runtime. Runtime is what in web development most of us really care about, because that's the speed that after, like, let's say a minute, 5 minutes, 10 minutes, that's the speed the program wants on your web server. That's the speed you want to have, but we have all this other crap in there. So why am I putting such an empathetic point on this? If you're in the Ruby community, you've probably seen the MJIT benchmarks or the release of MJIT, which is basically a fork of JRuby where a very, very intelligent and good person implements a JIT on JRuby, and they published their benchmarks. And as you can see behind me, the results are awesome. Like in a geometric mean, it's like 6 times faster than JRuby 2.0, and it's way faster than JRuby and Truffle or like the GraalVM and all of that. And so, well, here's a little disclaimer before I go on. Like, I really enjoy this work, and I think we should have a JIT in Ruby, and if the only way we get it into mainline Ruby is for people doing it on JRuby, that's fine, and I love all that work. And it's still very, very early work, so this work is in no way completed yet. But I have certain issues with this benchmark. Mainly because it was done like the benchmark I just showed you, the time something. And this is like a very, very good person. I think he's one of the maintainers of GCC or something, I'm not quite sure. But I have an issue with that benchmark, and so I want to show you again why and how. And another thing, lots of these benchmarks, they don't really mean anything much to me personally. Like there's stuff like the time it takes to write an instance variable, the time it takes to read it, an empty loop, an empty method call. Lots of them have like bit operations, not something that we usually do in Ruby. I picked this benchmark also because some of the benchmarks, so he used Graal version 22, and I did it with 25, and with 25, lots of these benchmarks were already slower when you ran it in the, let's say, incorrect way. But this one is still slower when I run it these days, and here it's one of the the slowest ones. So Graal is a third of the speed of JRuby, and I looked at this, and it's like, this cannot be. I run benchmark on this before, and that I don't believe that. So let's run it again, time, Ruby, and the script. And there we go. Truffle takes 33 seconds to complete that script, and MJIT takes 9 seconds. So obviously, it's way, way faster. Well, now, wait a second. Let's look again at what time are we actually measuring. First, startup time. Startup time to call an empty script in MJIT is 0 seconds. Truffle takes almost 4 seconds on my machine. That's time that we pay once when we run the server, so we don't really care about it. Next up, warm-up time. So I put it into like a proper benchmarking library, one that I happen to have written myself, that does multiple iterations and actually does a warm-up time. So for 95 seconds, it just runs the code without the result actually going into our final result. But I noted down all the runtimes, and I made you a pretty graph. So you can see that for the first iteration, GraalVM or like Truffle takes 28 seconds. It's super slow. But as you can see, as we keep going until the 14th iteration, it gets faster and faster. It goes all the way from 28 seconds to 2 seconds, while as MJIT starts off at about 9 seconds and just gets better to like 8 seconds. So that's quite a warm-up time, but we get so much faster as we keep going. And you can also see that sometimes it finds another optimization or another de-optimization, I don't know. I didn't run with debug, and it goes up in the 6th iteration. So this is just like one of my main point. Give the JVM, the GraalVM, the LuaJIT or whatever, give them warm-up times in your benchmarks. Otherwise, it's most likely, if you're a web developer like me and you care about the performance of your actual running server, it doesn't matter to you, and the results are likely very wrong. So lastly, let's have a look at the runtime. And I benchmark the iterations per minute, which luckily lots of you are already familiar with by now, iterations per second. And Truffle Ruby is about 3.7 times faster in the same benchmark. Like I literally just took the benchmarking code out there and put it into a benchmarking tool. So why am I telling you all of this? We just went from Truffle being 3.5 times slower in the original benchmark to it being 3.7 times faster when we only care about the runtime. So what's the moral of the story? And Piotr already mentioned that a lot yesterday. Run your own benchmarks. And I'm here to help you with that. So that talk is called Stop Guessing and Start Measuring. I'm Toby. You can find me on the internet as Practop. I work at a Berlin-based same-day delivery company called Leafery. We do Ruby, Elixir, JavaScript. We will also see a real-time or a real benchmark that I did at work. And yeah, what else do I do? I organize the Ruby user group in Berlin. I'm a Rails Goods coach. I do lots of open source, like an Elixir benchmarking library and UI code in Ruby. But I need to keep going because I have a lot of slides. So, what even is a benchmark? So, what is a benchmark? Sorry, if dizzy thing, don't look here. So, a benchmark is basically we take a couple of functions, just like these bunnies, and we try to feed them input, and we see like how fast can they eat the input. And as you can see with Ghost in the middle there, sometimes inputs don't quite fit with what the bunny wants to do or what the function wants to do, and so some inputs misbehave, and they're especially bad for a particular benchmarking function. And as you can also see about now, yes, Ghost jumped into the big bowl, so we also have to be very mindful and careful of resource contention, because if one benchmarking function, if we run in parallel or something else, takes up all the resources, the other benchmarks are basically ruined. So that is my short and easy guide to what actually is a benchmark. About this talk, lots of talks are either about a concept, which is then very general, but you don't know how to apply it in practice. And some of them are about tool usage, which are very specific to one tool, but again, then you can't apply them elsewhere. This talk tries to marry both of them, as luckily also lots of other talks here have. We're going to take a polyglot journey, so we're going to talk about JavaScript benchmarks, Elixir benchmarks, Ruby benchmarks, and about SQL benchmarks. So first, some small distinctions, benchmarking versus profiling. Profiling basically adds instrumentation and overhead to your program so you can see which function actually takes up the most time. That is very good to identifying the bottlenecks. It's not good for actually seeing how long it takes, because that instrumentation adds a significant overhead to what you're doing. Also, application performance monitoring is basically a benchmark that continuously runs on your application while it's in production, so it's good to identify where am I slow, but you don't want that to use that to develop like a new faster solution, because you don't want to accidentally make production 10 times worse. Lastly, or not lastly, but also very importantly, it's very important when you do a benchmark to give a system specification, like which GraalVM version were you running on, what machine, and all of that. Like, without that information, your benchmark loses a lot of its value. So, for instance, my benchmarking library tries to print out all the relevant information whenever you run it, so whenever you just copy and paste the console output, the information is all there. So one very important question when we talk about benchmarking is, what do we actually want to benchmark? And there's a couple of options: runtime, memory, throughput, or something custom. And all of them, of course, valid. One of my favorite custom benchmarks is the Phoenix framework, an Elixir benchmark, where they tried to increase the number of concurrent WebSocket connections that they could have on a single node. And they started off at about 100,000 and went all the way to 2 million. And that was just because they set the file limit handle to 2 million because they thought they would never reach it. Brilliant benchmark. It's a combination of everything. And if that's what you want to optimize for, you got to do that. You got to write your own benchmark there. We're going to focus on runtime, mainly because runtime is mostly what we care about, because it's faster for the user, and then the server is done handling, so we can scale better. But memory is also very important, but the tooling there is quite lacking still. And mostly we want to answer the question, did we make something faster? And now someone of you might come here and be like, wait a second, isn't that the root of all evil? I heard it somewhere, so it must be true. So in my opinion, not reading the sources is the source of all evil, and I'll show you why. So that sentence is there. It's in a paper by one of the fathers of programming, Donald Knuth, and there he says it, pre-measure optimization is the root of all evil. But wait a second. Let's read the very next sentence. Yet, we should not pass up our opportunities in that critical 3%. So he basically says it's very, very important as well, if it's critical. Also, in the prior paragraph, he says, a 12% improvement easily obtained is never considered marginal. So he tells us to benchmark, or well, not to benchmark, but to only do it in the critical path, and 12% improvements are enough because, as Piotr said yesterday, I don't care about 2% improvements. That doesn't matter. All the work you put into that is probably not worth it. So let's start with our first story about JavaScript. And at this point, we're going to talk about GoBots. So Go is an old language, and writing AIs that play Go is sort of a hobby of mine. So I've done it in 3 different languages so far. And when you do that, oftentimes you have to represent the Go field or the Go board. And so that you have to represent that I can put a stone there. And a very common operation is to check for your neighbors. So those are the neighbors of that stone I want to put there. So to see if it captures them, if it's even a valid move or whatever. Problem appears when you want to play in the corner, then suddenly only those 2 are your neighbors. But you still want to like report the other ones, or you got to have some sort of value to say like those are neutral fields, anyone could be captured by them. Sadly, that results in like lots of custom code. So for instance, here's our getColor function. And every time we want to get the color of an XY position on the board, we got to check, is this out of bounds? And then return neutral. And the is out of bounds function is done here. By the way, this is code I wrote 4 years ago, so I just realized that like that whole if is not necessary, and I'm sorry about that. But basically, we have to run through that Boolean condition all the time, which is a drag, and like every function that has to access something on the board, which is like a couple, but also the setStone function has to do that. So not cool. So what if, you know, we're clever people, what if we added an extra layer around the board? And then we fill this one with neutral values. That way, whenever I put a stone in here, I could just use my normal getBoard, and I get like all the correct values. So we go on, we refactor it. It's the best code ever because I have to throw away such a bunch of code. It's amazing. Now we write a benchmark with benchmark.js, and basically the most important thing is we add whatever we want to do, a function. We get like, okay, get the color of 1, 2 on that board, and then we have a couple of events where we then actually get the results. So we run that benchmark, and it's amazingly fast. So it's about like, the old version is 279 million operations per second, and this one is more than 1 billion and 800 million. So it's over 6 times faster. It's the best thing ever, right? So success, we did it again. As you can guess by the picture, maybe not so much success, because does it even matter? Is our end goal with our application really that we get the color the fastest way? No, it might help our end goal, but our end goal for a GoBot is to run as many game simulations as we can, because the more game simulations we have, the more input data we have, the better decisions our GoBot can make. So let's write a benchmark to see like how fast a game playout actually is. And here we do it for the 19x19 board, which is the best, well, the normal one, sorry. And we run this benchmark, and we see we actually got slower, about 20% slower. And why is that? Like, we benchmarked the other thing, we had the best idea in the world, how does that not work out? Remember, we made the board bigger, and in certain points in the playout, and especially in multi-colored research, we need to copy the board. And because a bigger board is way, way harder to copy, that takes more time than our small savings we did in the getColor function, because the getColor function is already very, very fast, so its absolute savings are very slow, are very little, but its relative savings were a lot. So it's about initializing and copying the board. So it's always good to not only run those micro benchmarks, but also bigger benchmarks that tell you, does this help my end result? So what am I measuring? Does it even matter? Is that really what I want to optimize for? And you've seen a good example of that yesterday, because a couple of days before the conference, we were arguing on Twitter about constant access in Ruby, and benchmarking it as you do. And I happen to say that, like, whatever we're going to do, it's most likely way slower than a database access. And Piotr noticed that I've obviously been reading his slides, and you saw that yesterday already, that database interactions are usually a couple of milliseconds, so whatever you do in the microsecond world often doesn't count when we talk about web development. So let's talk about some types of benchmarks, because I said these words micro and macro benchmarks, so what does that even mean for me? I like to liken that to the testing pyramid, which I hope most of you are familiar with, but we have unit tests, they test a single function, we have macro, or integration tests, sorry, wrong vocabulary, that test the interaction of a bunch of modules or a bunch of objects, and we have feature or end-to-end tests that really test the whole application. And that's the same with the benchmarking pyramid, micro benchmarks, macro benchmarks, application level benchmarks. As some small examples, those are known in Ruby. First, we have a micro benchmark for scoring, which is we take a board and we score the result of the board. That's a very micro benchmark. It's one single method. It does one job, micro benchmark. Macro benchmark is this playout that we've already seen in the JavaScript world. So this is my second Go implementation. And there we see how long does one playout take, and we benchmark that. And thirdly, we have application level benchmarks, which is for Go the whole Monte Carlo tree search. So it builds up a whole tree, and it goes like, okay, let's make a playout here, and then make a new node and make playouts here, and so on and so forth. That's really what we do, minus the CLI interface or the GTP protocol. So what does that even help us? In general, going from which direction? From your, stage right, your left, from left to right, the number of components involved goes up as we go to the other direction. Because first it's a little function, then it's more. But so does the setup complexity. So micro benchmarks are very, very popular because they're very, very easy to do. You just take one little function, bam, you have a benchmark, it's 10 times faster, you feel like the best person in the world. But setting up like a whole application with a database with actual data in it is much, much more difficult. At the same time, execution time goes up. Micro benchmarks are often in the microseconds, whereas application level benchmarks can be in the seconds or minutes even. At the same time, also the confidence of the real impact goes way up because, as I said before, one micro benchmark, like if regexes are 2 times faster, that doesn't mean that Rails or your web server is 2 times faster. It's maybe 0.01% faster or whatever, or 1%, I don't know. Also, the chance of interference goes up as you go to the application level because, for instance, the internet might be down or your database server might be overloaded, and that's not what you're benchmarking, but still it will affect your benchmarking results. Whenever someone shows you a graph like this, they will probably tell you that there's a golden middle, which is in the middle, and those are the macro benchmarks. Why are they so good? Because they strike a good balance. So what I often do when I benchmark a web application, I take a whole controller action, including the rendering and everything, and I just benchmark that. That's fairly easy to set up. I miss some things like the internet connection and maybe the middleware if I don't run it explicitly, but it's still very good, gives me very good results that I'm very confident have a real impact, but the setup time is not too big. So one of these application level benchmarks is that research of my own Ruby Go implementation. And those are some results there. So I run it with lots of different Ruby versions about once a year. I mean, I did it twice now to see like how fast are they. So we have a nice comparison of different Ruby versions that I did in, I think, January or February this year. So 2.0 is, of course, very slow. And we can see that the newest truffle version at that time is by far faster. You see it a bit better when you speed it up relative to 2.0, which is also the metric that MJIT used. And we can see that JRuby is about 8 times faster, but also JRuby with invoke dynamic is over 3 times faster, which is actually the goal of Ruby 3.0. So I like to joke that JRuby and JRuby are already Ruby 3.0. I ran that very quickly a couple of days ago with MJIT, and the results weren't anything breathtaking. But then again, MJIT is very, very early, and maybe they haven't optimized really objects and classes and all of that yet. So let's go to another benchmark, SQL, but with a little help from Elixir, because I don't actually have an SQL benchmarking tool. I use my own Elixir one. And this is a little story. So I was at work, I was having a good day, and suddenly it went boom. Our Bugsnag channel popped up, and I was like, oh, what's happening? And I logged into it, and I got an exception that says Elixir DB connection error. I looked at it, and it turns out that when you do an SQL query that's longer than 15 seconds by default, it times out. It's like, oh, 15-second SQL query, that's no good. So what happened? This is, damn, the GIF doesn't work. We have a courier tracker, which is the couriers that are driving for us are pushing their location updates live to a Phoenix server that we have. And it's very common that when you join the WebSocket channel, where that is, that you want to get the latest location. So that what was breaking. Give me the latest location that courier was at. So I was like, OK, I got this. I'm a pro. I know benchmarking. So let's write a benchmark. What we were using at the time is at the very top, which used a database view that just had the latest locations of all couriers, and then selected the one we needed. And I wrote 2 different versions that are not relying on the database view, but more custom, which is why they're called full custom, which we say basically, give me that courier with that ID. The difference between the lower one and the upper one is basically the upper one has like an array match, like it can have multiple courier IDs, and the lower one just has 1 courier ID. Sort them descending by time, limited to 1, and give me that 1. So I ran the benchmark. We had a bug, sorry. So we had 2.3 million locations as an input, because some courier was submitting their locations again and again and again, and we didn't yet do duplicate detection, which we now do. So I took that courier ID on an anonymized production dump and just ran with it. And so my new stuff is way faster. So I'm like, yay, good job done. I mean, I made it how many times faster? Like 200 times faster? Yeah. So best thing ever. Deploy it. Boom. And it goes like, oh, what the hell? And as I was Elixir DB connection, I was like, I fixed this. I did this. I fixed this. Like, why is the deploy not live? It goes Elixir DB connection error. And then like lots of them were like, oh, what is happening? I fixed this. I did the benchmark. I'm good at this. And so I roll back the release. I curse. I'm very, very sad. Everyone is looking at me weirdly in the office. And I'm like, what happened? So I go on and I write another benchmark. Well, actually, it's the same benchmark, but now I give it more inputs. The fun thing is, before I already wrote it with inputs, but I only had 1 input there. So inputs is one of my favorite features of Benchy, which I maintain and develop, is I can give it a map of multiple inputs, pass it in, and it will run each benchmark with each one of these inputs. So it's very convenient to use multiple inputs, because, as I said, functions can misbehave. And so we put it in there, and then every function gets one of the inputs, and we can use it. So run it again. And as we can see here, like our database view is the slowest when we run the one with 2.3 million locations. But for everything else, with 200,000 locations, 20,000, and no locations at all, it's the fastest one. The other ones get super slow, which is why we get that many errors. Because there's some couriers that have no locations at all because they don't use our application. And when they then take super long, it crashes, obviously. Yeah, our custom ones are fast for the many locations, but then they get to be slow. So what was the problem? I ran an explain analyze on the query, and we were having one index on courier ID and 1 on time, and was using the 1 on time to sort them descendingly, and then did a filter on the courier ID, so couldn't use both indexes at the same time. So what would happen if a courier would have no location? It would just have to scan through the whole list and then be like, oh, I didn't find it. And that's very, very counterintuitive, because usually when we do DB benchmarks, we just say like, okay, like give me the biggest table that I have, or like the most things that I have, and that should be the slowest thing, which was not true in this case. The fix is rather easy. I created a combined index of courier ID and time, so it can actually use both indexes. So another benchmark, and now we can see that our full custom version is by far the fastest one for every single scenario that I created and I put up here. Another caveat, if you do add indexes and everything, please always also benchmark the insertion or update time, because more indexes means that will be slower, and that's something that you have to take into account. For us, it got a little bit slower, but since we query them way more than we insert them, or well, we insert them a lot, but we still query them more, it was a good trade-off to make. What is the moral of the story here? Inputs really do matter. They are like the skyline behind me. They're very different. So for instance, I think for quicksort, the worst case input is either an already sorted list or reverse sorted list or something like that. That's something that you have to take to account for in your benchmarks. And also it might change on the size of the input, which is the fastest function. Another thing that's very important, you gotta have an interference-free environment. Sometime I ran benchmarks while Slack was running, and like they were half as fast. And so really like kill everything that you run on your machine when you run the benchmarks. Another thing is a correct and meaningful setup. You never find performance problems if you don't run with like in roughly production-sized database, because then n+1 queries and whatever will not affect you as much. Also, if you do a compiled language, do the -- release in Crystal or whatever it is in Rust, because otherwise all the compile optimizations won't really kick in. Also, don't run them in the development environment. So we created a special environment which we call performance in our Rails application. And that one is as close to production as possible so that we can still run it locally, and benchmarks are more than 4 times faster because it gets rid of all the caching, reloading, and what have you. And especially all the logging, because logging is often like the biggest mistake I see in benchmarks for web application frameworks, because when we log, and it's really fast benchmarks, that has a precise input or precise impact on the performance. So let's talk about Elixir real quickly before the time runs out. Tailcall optimization. I've heard that a lot, and I read that like when I learned Clojure, it was like tailcall optimization, best thing ever. You should always do tailcall optimization. I was like, okay, so tailcall optimization must be at least 5 times faster in my head than everything else, or tail recursive code. So we have an implementation of map here. One of them is tail recursive. This is the one we're looking at right here. And the other one is not tail recursive, it's body recursive, because the list prepend or append invocation that is here still happens afterwards. So we write in another benchmark, and again, we have different inputs, 10,000, 100,000, a million, and 5 million inputs, pass them in, and we run our map with the tail recursive version, we run the standard library map as a comparison, and we run the body recursive version. Then we go there, and we have a look at the results. Tail recursive is the slowest for 10,000 and 100,000. It's even like slower than our body recursive one, and body recursive is actually faster than the standard library map. But it gets to be the fastest with 1 million inputs or with 5 million inputs. So that's something, again, where that whole thing changes up. And here we can see another nice graph. By the way, Benchy produces these graphs with the HTML formatter along with histogram, box plots, and everything else, but I don't have the time to show them all off. And before we finish this talk, so what even is a benchmark in the end? And doing my second benchmarking library, this time Elixir gave me a very good answer to it. So this is like an official interface that you can use in Benchy. And so what is a benchmark? At first, we get a configuration. We initialize our benchmark with it. Then we gather some system data, like the Elixir version, the Erlang version, the CPU, the memory. Then we define the benchmarks. So we have this benchmarking job with this function. Then we measure it. So we populate what we have with the different runtimes or the memory usages. Then we calculate some statistics on it, iterations per second, median, standard deviation, all the stuff I couldn't talk about here, sadly. And then we take all of these results and we pass them into formatters. Benchy has a console formatter and an HTML formatter. And yeah, that's basically what a benchmark is. So I would welcome you all to enjoy benchmarking as much as you can and run your own benchmarks. Please, please, really do. Thank you.